Alright, ladies and gentlemen, we are here today with another physics problem here to solve, and today little Timmy has found himself in a detrimental situation. He is rolling at an unknown mass at 10 meters per second toward another rolling ball of uranium that's just 5 kilograms and rolling at 5 meters per second. We're not, of course, concerned with his safety or well-being. We're just here to answer some questions. So we're going to answer questions like 1 and 2. These two are a doozy. You kind of got to work them at the same time because we really don't know what little Timmy's mass is going to be after the collision, and we don't know what his mass is. However, we do know it's an elastic collision, so we can use some conservation momentum tricks. Here, let me show you. So, you know how it is. P equals mv. We're going to put little L's there for little Timmy, plus mu, V and U for uranium, equals ml vl prime. He's going to be, having a different velocity. Not going to move any mass though. And mu, also not losing any mass. And a v, u prime. He's going to be, that ball of uranium is definitely going to be traveling at a different rate after that collision. So let's take a look at what we already know. We already know this. This is going to be 7 meters per second. We're given that right there. And we are going to know this, 5 kilograms. Hit him with the 5 kilograms over here. Don't hit him with 5 kilograms. That'd be insane. And hit him with 5 meters per second over here. So we know this, but we don't know anything else. That's 2 variables. You might be asking yourself, Con, what am I going to do? There's 2 variables here. I didn't go to Diffie Q or any of that. You know what? Don't worry about it. I got you. So we're going to find the mass in terms of a velocity. We're going to find 2 in terms of 1. So we're going to go ahead and start filling in things. We're going to say mass of little Timmy, which is the, and we also know this, we do know this, velocity right here is going to be 10 meters per second. So there's your 2 variables that we don't know. We're going to do ml times 10 plus 5 times 5, going to give you 25. Nailed it. ml vl prime, we don't know that, plus, hit him with a 35. And so we can simplify that any, further. So we're going to go 10 ml, we're going to move this to this side over here so that, like terms, minus ml vl equals 10. And so, let's go ahead and factor out one of those mLs. We're going to get ml times 10 minus vl prime. And then, once we're there, we can start assigning some units. The units might get a little confused and you didn't see what was happening. So when you multiply the 5 kilograms times the 7 meters per second, let me put a little right there, you actually get some weird. Kilograms times meters, we all know, is newtons, so you're going to get Newton seconds. This is going to be Newton seconds right here. And so then we're going to find ml, mass of little Timmy, in terms of this velocity. We're going to do that by going ml right here equals 10 Newton seconds divided by 10 meters per second minus v L prime, what he's moving after. So we got this. This is going to be a very handy little equation that we're going to use just in a bit, because that's all we know right now is that, the mass number 2 is this. So now we're going to use a different type of conservation. We're going to do the kinetic energy conservation, because after all, it's an elastic collision, meaning there's no, thermal heat, any of that, no friction, I'm assuming. So we're going to go over here and separate it. We all know that the kinetic energy before the collision is 1/2 mv squared, which is kinetic energy. But the sum of all the kinetic energy before the collision equals 1/2 mass of little Timmy, which we know as this. So we're actually going to go ahead, instead of throwing an ml, we're going to throw in this whole big thing. We're going to throw in 10 Newton seconds divided by 10 meters per second minus VL prime. Throw that in some parentheses to not get confused. Actually, you know what? I'm going to throw that in some red parentheses because, you know, it's just easier that way. So that's our mass. That's the 1/2 times the mass. Now we're looking for that v squared. We know that our velocity before is 10 meters per second. We're going to go ahead and multiply that by 100. V squared, after all. Meters per second. Oh, that was bad. Let me clean that up for you. Meters per second. And we're going to do that plus the kinetic energy of the ball, which is 5 kilograms. We're going to throw that 1/2 in there. Oh, I just realized I'm writing in red now. That is a predicament. We're going to throw in that 1/2, 5 kilograms times 5 meters per second. So this is all before. And that's also going to be equal to what it is afterwards. So afterwards, it's going to be 1/2 mv squared again. But we don't know what our v velocity is, but we do know what our mass is in terms of the velocity prime. So it is going to be, once again, 10 Newton seconds divided by 10 meters per second minus velocity of little Timmy prime, the afterwards, times velocity prime, which is what he's traveling at afterwards, plus whatever the ball's doing. And we know that the ball's going to be going 7 meters per second afterwards, so we're just going to throw in another 5 kilograms. But this time, we're going to do it by the 7 meters per second. And actually, I just realized that I got to go back and square all these velocities. So I already squared that one. It was a quick little thing, you might have missed it. I need to square this, square this, square this. And once we got that, we can start solving for things. If you notice, we only got one variable in here. So let's start simplifying. We're going to simplify this bad boy. Start off by getting rid of these nasty little fractions. We're going to multiply both sides. Well, let's find the numbers that we already know. It's going to be 1/2 10 Newton seconds divided by 10 meters per second. You know the business. Times 100 meters per second. Plus 1/2 times 5 squared. 25 times 5. That is going to be 20. We're going to do 25 times 5 meters per second equals, same thing, 1/2 10 Newton seconds. I'm going to get tired of writing that eventually. 10 meters per second minus VL prime times another VL prime squared plus 5 times 7 squared which when simplified is going to give you 245. And also we're going to leave the half right there, 245. And over here we're going to get 125. So let's let me write that in red for you real quick. 125. Once again, we're going to do Newton seconds. Newton seconds. And so, I don't like these fractions, but there's an easy way to get rid of them. You just multiply everything times 2. Times 2, times 2, times 2, times 2. This is going to be a lot cleaner. I know, it looks messy, but just keep up with me. We're going to go 10 newtons. Then my handwriting doesn't help either. 10 meters per second velocity L, that, times 100, which is going to be 1,000 over 10 minus v. Oh, these are all minuses right here, right? Yeah. And so we are just going to keep carrying on. Times that 100. Once you simplify these, you are going to get 1,000 over 10 minus VL. We're going to drop the units for now, just make it look a little bit nicer. Plus, we already multiplied by everything by 2, so we're just going to get 125 equals the 10v squared. We're going to simplify that v prime and just hit a v squared on there, over 10 minus v plus 245. Now, doesn't that look so much nicer? We can use this right here to solve for v. So why don't we go ahead and do that? I'm going to draw a swift little line over here, make sure nothing's creeping its way in. And we're going to take this equation and go ahead and start using it. So let's simplify it even further. We are going to subtract 125 on both sides. So we're going to get 1,000 over 10 minus v of little Timmy plus 1. Nope, I'm sorry. We just subtracted 125 on both sides equals 10v squared over 10 minus v plus 120. So wouldn't you look at that? We got some like terms that we can get rid of. Not like terms, but we can get rid of these little fractions. We're just going to multiply both sides by 10 minus v. Same thing over here. 10 minus v. That's going to give us 1,000 equals 10v squared plus 120 times 10 minus v. And everything's divisible by 10, so why don't we go ahead and do that? We're going to get 100 equals 1v squared, or just v squared, plus 12 times 10 minus v. And all of a sudden it's looking a little bit nicer. So now we're going to move into that quadratic. Now this has become, a nice little quadratic equation. Distribute that, the 12 to the 10 and all that. And we're going to end up with 10, start moving things over, 10v squared plus 120 no, we are actually going to go even further. We're going to simplify it straight down. Since we got the v squared, we're going to go v squared minus 12v plus 20. Oh my god, I'm running into these things. Look at me go. But don't worry about it. We're getting there. So we're going to go v squared minus 12v plus 20 equals 0. Moved everything on one side. We got a nice quadratic to solve now. I'm going to scroll down, hopefully having a little bit more room to work. And we will find that you can actually simplify this to v minus 10 times v minus 2 equals 0. And now it's easy to see that v is equal to 10 or 2. So now we got to figure out why it's one or the other. It can't be both. But if we go back to this mass equation, where we found mass in terms of velocity, it can't be 10, because it would give us 10 minus 10 is 0, 10 divided by 0 can't divide by 0. I hear bad things happen once you do that. So we know that it's got to be 2. So we're just going to go ahead and write out in green down here, v LT prime equals 2 meters per second. And then we can go back up here, plug that in. 10 over 10 minus 2, 10 over 8, ends up your mass right here. Go ahead and write that in red. This is going to be the answer to 1, I believe. 1 was the one asking for mass. I was completely wrong. Yeah, I was right. 1 is asking for velocity, and 2 is asking for mass. Mass is, as we solved up here, 5/4 kilograms. And so why don't we go ahead and move on? What else is that? What else are we being asked for? We're also being asked for the average if the average force between LT and little Timmy and the uranium ball during the collision is 100 newtons, then how long does the collision last? Well, we know that, let's draw a swift little line right here. This is going to be 3, and we're going to start circling all our answers, just so they don't get lost. Wow, that was a great circle. And now we're going to be working on 3. Let's go back to black, and let's rock and roll. Number 3, we all know that force equals the change in momentum over the change in time. In regards to asking about this question, of course, the average force and how long it lasts. So we know it gives us that if the average force is 100 newtons, and that the change momentum is going to be equals, change momentum is P final minus P initial. And for uranium, the change in momentum was, mv 5 times 7 final, because that's the final velocity, minus 5 times 5, which is the initial. So delta P equals 10 newtons per second. You know how we found the newton per second up over here, right? Same thing. So you get 10 newton seconds divided by T, or delta T rather. And so, you're going to get 10 divided by 100. Change in time is actually only going to be 1/10 of a second. Pretty fast, if you ask me. Of course, you can see how the newton seconds divided by newtons gives you seconds, so that's why we're going to be left with this bad boy right here. That's the answer to 3. So let's move on a little bit. Let's go over here and work on, we are quickly running out of space here. Might have to erase some things soon. But we're going to work on 4. 4 is an easy one. So he's just trying to trick you over here. We're going to go up. We're going to look for what is the rate of change momentum during the collision. Well, we know that the rate of change momentum is delta P over delta T. So the rate of change equals 100, what he just gave us. So that was a pretty easy one. 4 is going to be, look, I'll even write it down over here. 4, right? This is how you do Roman numerals. Perfect. Equals 100 newtons. Circle that bad boy. Quick, let's go to 5. Good work over here. 5 is going to be, after the collision, how long would it take for little Timmy and the uranium to be separated by a distance of 50 meters? Once again, hitting us with the easy questions. Hits us with the hard ones first, leaves the easy ones for later. And so, we know that little Timmy, after the collision, is moving at 2 meters per second. Found that over there. And we know that the uranium is moving at 7 meters per second. So, if you do 5 meters per second times T, some amount of time, equals 50 meters. Because, you got the difference here, 7 minus 2. Hit them with the 5. And then solve for T. T is going to equal 50. No, I'm sorry, not 50. 10 seconds. Hit him with that right there. And now we find ourselves, I'll even label it for you. This is 5, right? Perfect Roman numerals. Now we're going to be working on 6, way over here in the corner. 1, 2, 3, 4, 5, 6. Perfect. I don't believe in that old fashioned Roman numeral system. I don't like it. Ooh, this is going to be an interesting one. After the collision, the uranium ball runs into a spring and compresses it until it stops. What spring constant will be necessary for the ball to stop at a distance of 1 meter? Let's check it out. So we know the spring equation, right? We're going to go 1/2 K constant with a compression of 1 meter squared is equal to the kinetic energy. You know, this is spring energy. We're going to set it equal to the kinetic energy of the uranium ball. We do that times 5 kilograms times 7 meters per second squared. We're going to simplify that one real quick. 1/2 K times 1 meter. 1 squared is 1 equals. Once you calculate all this out, you're going to get 122.5. I won't show you how to press those buttons, but once again, it's going to be Newton seconds. We're going to go ahead and multiply both sides by 2 times 2 times 2. We're going to get K, or equals. We're also going to divide by 1 on both sides, divide by 1 meter. And so you know there's a kilogram meter in here, so when you divide by 0, you're going to get just seconds after multiplying and all that. I mean, you're still going to get the Newton meters and all that. But yeah, once you multiply by 2, divide by the 1, you're going to leave K by itself, and it's going to be 245 newtons per meter for that K constant right there. That's pretty strong. And once again, if you were confused, that is number 6 right there. Love me some number rules. But yeah, remember, this is chaos science. We do science chaotically and disorganized. It's kind of some people's things, you know, whether you take it or leave it. But come back, subscribe, like, leave some comments, what I should do better and all that. And I'm always open to criticism, unless it's negative. I don't believe in that. Tune in next time for whatever someone decides to throw at me, I guess. Goodbye.